Greetings. We've been looking at voltaic cells, otherwise known as galvanic cells, and here's an example here. If we were to look at this particular cell that we have and treat it as a voltaic cell and wanted to know, okay, how is this going to be set up? Which directions are the electrons going to flow? We would have to consider the possible reactions. We've got copper and zinc electrodes. So one of the possible examples is that copper could be reduced. The other thing is that the zinc could be reduced. And looking at these standard reduction tables here, we would see that the copper is the more positive value, so therefore it has the highest driving force to be reduced. So that means that our copper side, we're going to see reduction happening. Remember, reduction is gain. And that means the zinc would be oxidized. It would be losing the electron. So in that case, this cell, the zinc would be the anode, copper would be the cathode, and our electrons would flow, in this case, to the left side, to the because always flow from the anode to the cathode. Now, if we were to change this and actually take this thing, which on its own is going to occur in that direction, but apply a voltage source to this particular cell, and if we hooked it up in such a way to have our voltage source to have the positives and negative side of our voltage source switched, we could actually force the electrons to flow in the opposite direction. And if our voltage source was strong enough, and if it had enough voltage to it, it could actually resist that natural flow. We just saw it naturally wanted to flow to the left side, but if our voltage source was powerful enough in the opposite directions, we could actually force the reverse direction to have the reverse reaction. Then it spontaneously would go. So we could force the electrons to flow this way. So that means that doing that, we'd actually have the opposite reactions occurring in each cell. So instead of copper being reduced and gaining an electron, by applying this voltage source, we could actually force it to lose the electron. So we'd have the reverse things happening. Now, the solid copper is now going to go back into solution, okay, and the zinc is going to go back into solid. So this would be what we call an electrolytic cell. And what we're essentially doing here is we're basically recharging this battery. We've plugged it in. It makes that reverse reaction occur. And just like a rechargeable battery, when you plug it in, it makes the reverse reaction occur. And then when you unplug it, the spontaneous reaction occurs in the opposite direction. So for example, if we look here, here we have a voltaic cell of identical components on one side, but here we just have it set up on its own. It's not plugged in or anything. And in this example on the left here, the spontaneous reaction has our electrons flowing from left to right. And so we get a voltage of 0.74. That's a galvanic or voltaic cell that's going to occur in that direction. However, if we take this same voltaic cell and we hook up a power supply and hook it up in the opposite direction, as long as we apply a voltage from our power supply of greater than 0.74 volts, it's going to be strong enough to actually force the electrons to flow the other way. So that is an electrolytic cell. So like I said, this is how a rechargeable battery works. We plug it in, we force the electrons to go in one direction, so we're essentially causing the reverse reaction to occur. Then we unplug it. Well, the spontaneous reaction is in the other direction. And so we see galvanic cells, voltaic cells, they are spontaneously occurring, whereas an electrolytic cell is a non-spontaneous reaction. We need to have some type of an external power supply, some external current to force that reverse reaction to go. Okay, so big difference. Electrolysis or electrolytic cells are reactions that are non-spontaneous. They have to have that external power supply to get them to go. So let's take a look at some examples of this. Let's say we had some molten NaCl. So we're not talking about solid salt. We're talking about taking that solid salt and not putting it in water, but we're actually melting it. If I were to take that and apply that to a voltage source, I could get some reactions to happen. Now let's think about which reaction would happen on which electrode. Well, we have some liquid NaCl, which is an ionic compound. And when I apply that voltage source to it, the way we have it configured here, we would set the electrons to flow this way because they're always going to be coming out of the negative side into the NaCl. So we think about what would be happening at each electrode. Well, since my electrodes are flowing towards the right, that means we would have reduction happening on this side. This side would be gaining electrons, and then the opposite side we'd be having oxidation happening. So let's think, well, which would be occurring, what reaction would be occurring at each side? Well, think about who would want to be reduced. Well, the species that we have in there, it's an ionic compound. So we write it as NaCl, but it's actually sodium ions that are connected to chloride ions. So we think about, well, who would want to gain electrons and who would want to lose electrons? Well, sodium has a positive charge. It's already lost one electron. Now it has an octet. It's not going to want to lose any more electrons. That sodium is going to want to have more of a better tendency to gain that electron to get back to neutral. So the sodium is going to be the species in here that's going to want to undergo reduction. So this is the equation, the reaction that would happening on this electrode. Whereas the chloride ion that we have in here, well, that is negatively charged, so it has an extra electron already, so that's going to be the one that's going to undergo oxidation most readily because it has that extra electron to get out. So that will be the reaction that will be happening on that particular electrode. Okay. And so what we would have happening here is if we put this in our molten salt, again, we've taken salt, we've melted it, we can actually get the element sodium. See, well, how do we come up with the element sodium? Because the element sodium is pretty reactive on its own. You're not going to find it in nature. Get some salt, and you can do electrolysis, and you can actually get the element sodium to be a product because that's what's going to be plated on this electrode. On the other side, as you can see, where we have the oxidation occurring at the anode, you can see that we're going to actually be making chlorine gas. So we would see bubbling happening on this side. This electrode would probably be made out of some inert electrode like platinum or something. It's not involved in the reaction, but we get chlorine gas being produced on that side. So that's an example of electrolysis, which is an electrolytic cell. So this is very important. A lot of electrolysis is used in industry. Like I said, it's how we can make sodium, it's how we can make chlorine. It's actually how aluminum is made. This process here, they were able to take the aluminum oxide, which is in bauxite, which is mined naturally in rocks. And we can take that aluminum oxide compound, we can use electrolysis, and we can separate it into aluminum and oxygen. That's one of the ways that we get aluminum to be made. So let's take this same example, and we were looking at just melting these ionic compounds, but what if we had aqueous solutions of this ionic compounds instead of just melting them? So let's say that we had some sodium fluoride, but this time it's an aqueous solution of sodium fluoride. So we've hooked it up to our power supply. We have our flow of electrons going in that direction because the external power supply is just forcing them in that direction, which means we'll have reduction happening on the right and we'll have oxidation happening on the left. So we want to think, well, which reaction is going to happen on the right? Who's going to undergo reduction? Well, let's think about which species we have present in our cell. We have the ionic compound sodium fluoride, so that means we have sodium ions and fluoride ions, but we can't forget the water. It's an aqueous solution, so we also have water molecules. So let's think about, well, who could possibly want to be reduced? Sodium, would sodium want to be reduced? Remember, reduction is gain. Would sodium possibly want to gain an electron? Well, sure it would. It's a good possibility. It's positive. Gaining an electron would get it back to neutral. So that's a possible reaction that could occur at that electrode. Would fluorine want to gain an electron? Well, it's already got a -1 charge. It's already gained an electron, which actually gives it an octet. So we're not even really going to consider that. That's not going to be very feasible. It's not going to want to gain an electron. The other possible option is water. It's neutral, so it's possible that it could gain an electron, and when it would do that, we would end up with hydrogen gas and hydroxide. And this is one of the equations that's on your standard reduction potential list. So you can just see water on this side. When it gains an electron, This is what we get in our equation. Now, so we have a couple possibilities here that could happen at that electrode, and we need to see which one of these actually would happen. And to do that, we have to look at their standard reduction potentials. So if we look up the reduction potential of the sodium, we see that it's negative 2.71 volts, whereas the equation for the water, it's kind of towards the middle of your table there, is 0.83 volts. And remember, well, which one's going to undergo reduction? Our rule is the more positive value is the one that's favored for reduction. So the more positive value here is the water. So we actually will not be forming the metal sodium. That top reaction is not going to occur here because the reduction of the water is going to be favored. That's the one that's going to occur. The sodium will actually just stay as a spectator ion in here and not do anything. Now let's take a look at the other side of things here, at the oxidation. Well, let's think who could possibly undergo oxidation. Oil. Oxidation is loss. Who's going to want to lose an electron? Well, sodium is +1 right now. It's already lost 1 electron. It has an octet right now, so it's not going to want to lose another electron, so I'm not even going to consider that as a possibility for oxidation. Would the fluoride ion want to lose the electron? Well, it does have an octet, but it's got a negative charge, so losing an electron would get it back to neutral. So that's a possibility. It might undergo oxidation. Again, we also have water, which is neutral, so it's quite possible that water would lose an electron. And again, here's a second equation. Notice there's two different equations you have on your standard reduction potentials that involve water. One of them involves gaining, and in this case here is what would happen if it were to undergo oxidation. So again, we want to think, well, which of these reactions is more likely to undergo oxidation? So we look at our standard reduction potentials. Now in this case, we're talking about oxidation. So it's the opposite here. So in this case, the more negative one is the one that's going to undergo oxidation. So in this case, our more negative value is the reaction with the water. So that's going to be the reaction that happens at the anode and undergo oxidation. So in this case, even though we actually had sodium fluoride in this cell, they're actually just spectator ions in this whole thing. We're not going to be making fluorine gas. It's not going to happen. We can see it's not as favorable as the water. So we're actually going to be making hydrogen and oxygen is what's going to be produced at each electrode here, because we can see when we look at the potentials that that's the reaction that's going to occur. The NAF is just a spectator ion. It's there to help conduct the electricity, but like I said, you can see hydrogen will be produced on the right side here. We'll see bubbles, and we'll also see bubbles being produced on the left side. That will be where our oxygen gas. And you may remember we did the electrolysis of water. So a lot of times I put some kind of an ionic compound in there just to help it conduct electricity, but in a lot of cases, depending on what I choose, it's just going to be spectator ions. Okay, so we looked at the electrolysis of molten liquid before and say, okay, well, we saw that we actually could produce the element sodium and the element chlorine because in that case we had the molten salt, and so in that case these are the two reactions that happened. And so at the cathode where we had reduction occurring, we were actually making the element sodium. So we were actually splitting apart our salt into sodium and chlorine. Those were the products we got for pure molten liquid sodium chloride. But what if we had aqueous sodium chloride and we tried the electrolysis on that? What would happen in this case? Well, in this case, let's think about the species that are present. Well, we still have the sodium ion, just like the molten. We still have the chloride ion, just like the molten, but we also have water. So we need to look at all the possibilities to see what would actually happen at each electrode. So who's going to be reduced? Well, again, sodium might want to gain an electron, but this time we also have water that might want to gain the electron. There's our same equation we just saw a minute ago. So which of these will be favored? Well, if we look at the reduction potentials, again, the more positive is favored for reduction. So that means actually the water will be reduced, and we will not be making sodium on this side. On the anode side, where we're going to have oxidation occurring, let's look at our possible options there. The chloride could possibly lose the electron, but again, we have water present now. The water could possibly lose the electron, Which of these is going to occur? Well, so in this case, since we have oxidation occurring, it is the more negative value that is going to win and be favored. And so in this particular case, it's the water that gets to be oxidized and not the chlorine. So once again, the sodium chloride, when it is dissolved in an aqueous solution, the sodium and the chlorine are just spectator ions. We can see from looking at the reduction potentials that we're actually going to be producing oxygen gas and hydrogen gas instead of making sodium metal and chlorine gas. So again, these are electrolytic cells. Electrolysis is a pretty big deal. And another application we have of electrolysis is the fact that a lot of times we can have active electrodes. Remember, active electrodes are when the metal that the electrode is made out of is actually involved in the reaction. In this particular example here, at our anode, we have the zinc metal. The electrode is made of zinc, and so the solid zinc is actually going into the solution. So our mass of our zinc electrode is going to go down as this reaction progresses, and in this case, the copper is being formed on the cathode here, and so the mass of that would go up. So one thing that they use this for, besides separating compounds like we just saw with the sodium chloride and the aluminum oxide, is sometimes they use this to electroplate things, because the solid copper is actually going to be forming on that copper electrode. And so a lot of times they'll take a metal that is more reactive. Maybe they'll take an electrode that is made of iron, and they'll put it in a cell and actually get something like nickel to deposit on it, something that is less reactive. Or they'll use chromium, which is they'll chrome plate something. And so not only does it look prettier in some cases, but they're trying to get an outer layer of something that's less reactive to try to prevent corrosion. So electroplating is just an example of an electrolytic cell where you have an active electrode. And here's just another example of nickel plating something. So we can apply the voltage source in one direction, and we can get some of the nickel from solution, some of the nickel ions, to form solid nickel, and they are going to form on that electrode and plate it. Okay, so finally I have an example I want you to look at. So in this case we have some aqueous silver fluoride, and we have it hooked up to a voltage source, and you can see from our picture we're using that external power supply to force the electrons to flow in this direction. So our question is this: we are in an aqueous acidic solution. So what I'd like you to do is, after you read these directions, pause the video and figure out which half reaction is going to occur at which electrode, what's the overall equation for the reaction, and then also figure out what is the minimum external EMF. Remember, EMF stands for electromotive force. It's essentially what's the minimum voltage that we would need to cause this reaction to go under standard conditions. Without a power supply, it would not go in this direction. It's not spontaneous in this direction. So we need that power supply, and that power supply needs to have enough voltage to force the electrons in this direction. So the question is, what is the minimum voltage required to do that? So pause the video now, figure it out, and when you're ready, hit play. Okay, so in order to answer this question, we need to look closely at what species we have present in our cell. Since it's silver fluoride, an ionic compound, it's aqueous, and it's in an acidic solution, the species that we have present are the silver ions, the fluoride ions. It's aqueous, so it's in water ions, but it also is in an acidic solution, which means we have some hydrogen ions present as well. Depending on what acid, it might be chloride as the negative ion. We're going to assume here, since it didn't tell us, that that negative ion is a spectator and not important. Okay, again, looking at the direction of the flow, we know we'll have reduction happening on the right side and oxidation happening on the left. So let's figure out what our possibilities are. Who could possibly be reduced? Remember, reduction is gain. Who would want to gain an electron? Well, certainly that silver ion is a good candidate to want to gain an electron. Fluorine, not so much. Water's a possibility. It could gain the electron. But we also have a hydrogen ion, which could possibly want to gain the electron. So who's going to win? Well, we look at the standard reduction potentials, looking them up on our chart. And again, we've written this in terms of reduction. And so our rule is the more positive value wins. So in this case, we actually see the silver wins. So we actually would be forming some solid silver. So in this case, when we ran this guy, we would be silver plating this electrode. We would get some solid silver forming on the outside of that. It'd be a way to silver plate something. Looking at the other side, who would want to lose electrons? Oxidation is loss. So, well, fluorine has an extra electron. That fluoride ion could lose it. Again, water could lose the electron. And really, those are the only options. Everyone else has already lost one. They're positive. They have octets. So who's going to win out of these two? Well, we've got our positive 2.87 and our positive 1.23. But since this is oxidation, it is the opposite. So the more negative one wins. So in this case, the water will be the reaction. Water gets oxidized in this case. So overall, my two reactions that will be occurring at the two electrodes are those. We've simplified this here for you. And now to answer the question, well, we said this does not occur spontaneously. We need some power supply to do it. So what is the voltage we're going to need to force them in this direction and to force this reaction to occur? Well, to do that, we can look at our cell potential equation, same equation we've done before for voltaic cells. So we have the cathode minus the anode. So looking up our values, we have our cathode, which is the silver, which is 0.80 volts, minus the reduction potential of the anode, which is positive 1.23 volts. So we pop that into our formula, and we get negative 0.43. Wait a minute. We've always gotten positive values for voltaic cells. Well, remember, voltaic cells are spontaneous. Electrolytic cells are not. So we're going to get negative values here. And what that tells us is that is the amount of voltage that we are going to need to force the reaction in this direction. On its own, it's not spontaneous. So we actually need to supply at least or more than 0.43 volts. It's going to force them in that direction, and then the reaction will occur. So hopefully you were able to figure that out, and we're good to go. And that is our little lesson on electrolytic cells. Thanks for watching.